Welcome to Lecture 27A. This is a two-part lecture series. In the one case, we're dealing with the divergence theorem, but now we're going to look at an application where we're dealing with delta functions in 3D. And in the second Lecture 27B, we'll look at a superposition problem. So the material for this lecture comes from reading Assignment 5. Section 3.2, which is dealing with cylindrical geometry, and section 3.5 and an additional problems in section 5 that deal with Dirac delta functions. So the objectives for this particular lecture are the application of the divergence theorem for an electrostatics problem, assuming a Dirac delta function for the source term rho. The concepts and visualization skills are to develop procedure for determining the field for a cylindrical symmetry example where the source consists of a filament and a sheet, and also just to introduce or reintroduce the principal superposition. We'll not exploit to an extent in this lecture, but in the next lecture we'll go into more details. As usual, the second slide is the summary of the slides to follow, so we will just move on. All right, so this is sort of a similar slide to what we had when we dealt with just a cylindrical geometry. So I'll just go through it very quickly. This is for the case of a Dirac distribution example in terms of characterizing the charge density, which is the source term, and this is for an irrotational field problem. Here we're going to assume a homogeneous medium, and so homogeneous means that essentially any constants are just scalars. They don't depend on position. And as we saw in a previous lecture, typically we would work with field quantities, and so we could have a displacement vector D, or we could choose a vector, vector E representing electric field, and so we could either use this pair or this pair, right? In our case, to sort of reduce the clutter, we're just going to call D F, and we're going to call rho subscript E as rho, just to keep things simple. So it's understood whether or not we're going to be using D or E as part of the problem, or at this point it doesn't really matter that much. So we're going to use F instead of D, in which case this would become the curl of F equals 0, and the divergence of F would be equal to just plain rho. All right, so just recall the divergence theorem. The left-hand side is basically an integral over a closed surface, the dot product between two vectors. That's equivalent to taking the divergence of the vector field and integrating over the volume that's enclosed by that surface. Now, because we have these relationships here, the divergence of F is equal to rho, that means this integral just becomes this integral. And typically the rho is given, and therefore if we can compute the right-hand side, we only need to figure out how to extract F from this expression. And under conditions of pure symmetry, of symmetry in the problem, and in fact this becomes possible to do. So let's look at the problem statement. We have a cylindrical shell of infinite length with radius r, and a surface charge density sigma is concentric with an infinitely long filamentary wire with line charge density lambda. So if you look over on this side, this base is a trace. So effectively this circle that you see is nothing more than a cylinder that projects into the z and minus z direction. And its surface charge density, which would be coulombs per meter squared on this exterior cylindrical surface, would be sigma. And this is a filament located at the origin, and its charge density is lambda, which means, and it'll be a constant. It's basically per unit length in the z direction. So this is more or less the geometry we're dealing with. And both of these, the shell and the filament, are aligned with the z-axis. So we want to compute F. And so the procedure is first determine the nature of the symmetry and determine if superposition applies. In other words, sometimes it's not necessary to use it. In other cases, you have no option. Second is to establish the form of F and establish the shape of the Gaussian surface. So this is more or less taking the symmetry into account and then exploiting a Gaussian surface that basically is amenable to that particular geometry, symmetry. Next would be to compute the left-hand side of the divergence theorem, followed by the right-hand side, and then equate the left-hand side and the right-hand side to compute the vector field F. All right, so let's look at basically now the charge density and the superposition principle. Just sort of, let's see how this sort of comes about in this problem, even though in this case we're not going to apply superposition, but you can see where effectively it can play a role. So we're going to represent the charge density. So we have a filament, we have a surface charge. And so if you look here, for instance, row of 1, you could represent a filamentary charge either in Cartesian coordinates, which means delta x, delta y, because the filament basically is in the z direction. And so as far as a cross-section is concerned, the Dirac function is only in the xy plane, and this lambda represents the charge density per unit length, coulombs per meter. On the other hand, we could also represent this in cylindrical coordinates, in which case it would take on this form. For the cylindrical surface, it's a sheet, right? That we would have basically, the only option here would be basically to use a cylindrical coordinates to describe what the delta function would look like. And so in this case, for the surface charge on the cylinder of radius r, it would be delta of r minus r times sigma, sigma being the charge density per unit in terms of coulombs per meter squared. If we were to add these two together, and of course here we must essentially stick with the same coordinate system. Here I've just shown that Cartesian could be used to describe row 1, but actually since here we need to work with cylindrical coordinates, we'll use the cylindrical coordinates version for row 1 as well. If we add these two together, this basically represents the total charge for the system. All right, so let's look over here now and look at what the principal superposition tells us. We need to divide it into two subproblems and then add it together. So one subproblem would be just look at the filament, and another subproblem is just look at the cylindrical surface. So for this case, we would have the curl of F1 equals 0, and the divergence of F1 is rho 1. For this case would be the curl of F2 equals 0, and divergence of F2 equals rho 2. So these are two independent fields, each one of them basically resulting from a different charge density. Now let's take the sum of the two fields, which is superposition. Okay, if we take the sum of the two, and if we take the curl of both sides, curl of F1 plus curl of F2, because this is a linear operation, this is equivalent to the curl of F. And because this is equal to 0 and this is equal to 0, then the curl of F is also equal to 0. So this is for the total field. Divergence, we can do the same thing. It's a linear operator, so divergence of F1 plus divergence of F2 is equal to the divergence of F. But the divergence of F1 is equal to rho 1. The divergence of F2 equals rho 2. But rho 1 plus rho 2 equals rho. That's the total charge, which is this total charge that we see here. So we could either have solved this as two independent problems, sum the fields, or in this case, because we have basically both the filament and the cylindrical sheet have basically the same axis of symmetry, we can basically solve this as just one common problem, right? And so in this particular example, that's what we're going to do. We're not going to apply the principle of superposition. It's just an extra load of work. We can just take the total charge as a whole and solve this problem. All right, so this is an interactive visualization of the Gaussian surface. So this T basically allows you to move this Gaussian surface in and out. This Gaussian surface has a top face, a bottom face, and the exterior cylindrical surface. And so you can play with it. The black line that you see here is this infinitely long filament with a line charge density of lambda, and this yellow is the surface charge, the cylindrical surface charge with surface charge density sigma. These gray arrows that you see here are unit vectors, and these are basically the field. A vector representing a unit vector, so it's the field divided by the magnitude of the field. And the height of the Gaussian surface is capital Z. All right, so if you want to play with this, you'll see what happens is this Gaussian surface basically goes in or out. So for instance, at this point, the total charge enclosed would be everything that's on the filament and everything that's on this surface. If you bring this in and you go inside this radius of r, then the total charge enclosed will no longer include the component due to the cylindrical surface. It'll only include the component due to the filament. All right, this is just a reminder that you might have learned about Gauss's law in ECE 211 0, which is the principle we're applying in this problem. Here, the total charge enclosed, which is the right-hand side of the divergence theorem, will come from both the filament and the sheet based on the way the Gaussian surface is drawn here. The use of Gauss's law will be further investigated in EC 221, which is the Electric and Magnetic Fields course, next semester. All right, so now let's basically compute the left-hand side. So we know basically that the field has radial symmetry. So we can write f out in this form. So this is f is some function of r. This is a unit vector which represents the r hat direction. So there's no z component because in cylindrical coordinates r is parallel to the xy plane. So we're going to use surface parameterization here for the external cylindrical surface. X equals r cos theta, y equals r sine theta, z equals z. This is the range on theta, and this is the range on z. The height of the Gaussian surface is just capital Z. So if we basically put this together, then we end up with this for the position vector that maps out the surface of the cylindrical surface of height z. And then we need to basically compute the differential surface area vector. So first we take a derivative of the position vector with respect to theta, and we get this result, which we'll call the t theta hat vector. And if we take now the derivative with respect to z, then we get this vector, which we'll call the tz vector. If you take the cross product of these two, which means you just put this in a determinant form, first row being unit vector, second row being t theta hat, and the third row being tz hat, we end up with this result. And we have to check to make sure that this vector is pointing outwards, because the divergence theorem says the surface area vector should be pointing outwards from the surface, and turns out this is agreeing with the convention. So we do not have to multiply by -1. All right, so N1 ds1 for the exterior cylindrical surface is just t theta hat cross tz hat, tz bar d theta dz, and you end up with this as being the expression. Now what we have to do is evaluate f on that surface, and so that surface means that x will become r cos theta, y will be r sine theta. So we plug these two into this expression here, and we end up basically with this representing f, which is now purely a function of theta and r. And so now we just put in the value of f here and the value of n1 ds into this surface integral, and this is integrated over the exterior surface of that Gaussian surface. That's the cylinder contribution. And f of r will come outside because the integrals with respect to theta and z, and so this is just a constant. If you take the dot product here, this will just give you r d theta z, and we end up with 2 pi r z f of r. Notice this is exactly the same expression that we dealt with in the previous case when we dealt with just a pure cylindrical geometry. And this, of course, is just the surface area of the Gaussian surface, the cylindrical surface itself. All right, so the various left-hand side possibilities of the divergence theorem for different geometries can be found on the fourth last slide of lecture 26. Make sure you know how these left-hand side expressions came to be. All right, so now we basically have to look at rho because we're going to move to the right-hand side. So how do we represent rho? Because we need Dirac delta representation. And so here, for instance, for the filament, we can either represent it this way in terms of Cartesian coordinates or this way in terms of cylindrical. As we mentioned earlier, since basically for the exterior cylindrical shell, we need to use cylindrical coordinates, we basically have to make sure we stick with the same coordinate system. So we'll be using this formulation for rho, dealing with the filament, and this formulation for rho when we're dealing with the cylindrical surface of radius r. And the units are given here as well. All right, so we are now in a position to compute the right-hand side of the divergence theorem, which is the triple integral of the charge density integrated over the volume enclosed by the Gaussian surface. And so in this case, since we have a filament, which is here, and we have basically also a cylindrical charge with a surface charge distribution on it, the Gaussian surface corresponds to a cylinder with a top and a bottom face and an outside circumferential surface. But the only one that makes a contribution to the flux is the outside circumferential surface. And so essentially, we're interested in that surface. However, since we're interested in computing the charge density within the volume contained within the Gaussian surface. We need to be careful in terms of how we do the computations of the right-hand side. So, for example, on the inside of this cylindrical shell, which actually is radius of capital R, that's from any distance, radial distance from 0 to R minus delta R, which would be just on the inside surface cylindrical shell. Then what we're integrating is a charge density that's represented by the filament. But we've already determined what that is for a filamentary discharge. It's basically the term that we see here, which is lambda over pi r prime delta r prime. And we're integrating this from 0 to r, but r basically is up to r minus delta r, that is the inside of the cylindrical shell. And then since we're dealing with cylindrical coordinates, then the differential volume is just dz r prime d theta. The height of the Gaussian surface was z, capital Z in the z direction, and we're going once around the loop. That's theta of 0 to 2 pi, and so this is the integral that we're computing, and that this is valid basically for any value of r from 0 up to r minus delta r, and gives you lambda times z. Now recall that when we're integrating in cylindrical coordinates, the delta r prime dr prime, we're basically only integrating over half space 0 to r, not from minus r to r. So that means that this delta function integral is not 1 but 1/2. Okay, so this is only a case when we're dealing with spherical coordinates. And cylindrical coordinates, when we're dealing with filaments, point sources, and the like. All right, so this basically is what we end up with. And so now the question is, well, what happens when we move outside the cylindrical shell? So for instance, this is the Gaussian surface on the inside, but exterior to the filament. And this here shows the condition where now the Gaussian surface is outside the cylindrical shell. And so in this case, since the volume integral basically is the total charge enclosed, it means that we have to basically make sure we pick up the value of this, having gone from 0 to r minus delta r, which is basically the term that you see here, which is this term. And on top of that, now we go from r minus delta r to some value r greater than r plus delta r, in other words, in this direction outside. In that case, we're dealing with the cylindrical charge density, surface charge density, so the appropriate direct delta distribution is sigma delta r prime minus r. Again, this is the differential volume cylindrical coordinates. Again, we're dealing with z as being the height of the cylindrical box. But here the lower limit is r minus delta r, and this r is any value greater than r plus delta r, again from 0 to 2 pi. If we do this integral, this basically will just become 2 pi, contribution for theta. Delta r prime minus r prime dr prime basically just means that we're sampling r prime at capital R, so that basically produces the r value that you see here, and then sigma and z. So we end up now as being that having this value for values r greater than r plus delta r. So that more or less basically completes the calculation of the right-hand side. Just a general note here that the problem can be solved as a whole, since the cylindrical surface shell and cylindrical filament share the same axis of symmetry. And so basically, we can basically treat as one uniform system. And if we want, we can basically stay in cylindrical coordinates in terms of vector representation and add things accordingly. But in this case, it's not a problem. But we could have also solved this by superposition, by first solving the filament problem and then the surface shell problem, and treat them as two independent problems, and then summing the two resultant vector fields. We could have also gone that route. So the next step basically is to make the substitutions and equate the left-hand side with the right-hand side and compute the field F. So here we basically have just taken from the previous slide the expressions for the case 0 is less than r is less than capital R minus delta capital R. And we obtained this result, 2 pi r z f of r. And on the right-hand side, we had delta z. So this corresponds to this side, this corresponds to this side. For the region r greater than r plus delta r, we had this result, this of course is still the same, left-hand side doesn't change, equals lambda z plus 2 pi sigma rz. And so here we can solve for fr, and here we're solving for fr, just dividing through by 2 pi r capital Z on this, for this side, and 2 pi rz also on this side. We know that this is the magnitude of the field, and we know the direction is in the radial direction, so we can just then write out the vector expression as f equals lambda 2 pi r hat for the condition 0 less than r less than capital R minus delta r, and for the condition r greater than capital R plus delta r, the field is basically the magnitude here, r hat vector. Okay, so the next thing then we can do is just to graph the result. So in graphing the result, we basically are using specific example here, sigma's 1, lambda's 2 pi, and r equals 1. And so up to capital R, which is the inner surface of the cylindrical shell, we basically have a 1 over r dependency, and then you see a sudden jump, and this is the contribution that's produced by the cylindrical shell. We now basically have 2 over r. All right, this concludes lecture 27A. Thank you for listening.